Hi, my name is Abigail Wilkins, and this is in part for an application for Mates Elementary for the science specialist position. So today, we're going to talk about circuits. Who has seen one of these before?
Me.
Okay, what is it? What does it do?
Charger.
It's kind of, well, it doesn't have to be a charger, right?
iPad charger.
An iPad charger? Yeah, an iPad charger has this on it. What else? What else can you plug in with this? Constance? Anything, right?
Light bulb.
Light bulbs, hair
It could be like thing
dryers.
to make it for like hair dryers.
Yeah.
To make,
Power.
light up a light bulb or like for a lamp or for a fan or something.
Yeah, perfect. Yeah, you can plug anything in with it, right?
Yeah.
So what have you noticed about these? Describe it to me.
They have electricity.
They have electricity. Constance?
They have two prongs with holes in the middle.
Prongs with holes in the middle. Why do you think there's two prongs on here?
And why
To
is
get
it
the
plastic?
electricity from the wall and through the cord into the
I know why.
device.
Perfect.
I know
So why
why
don't we
it's
just
not-
need one?
I know why
Yeah.
it's not metal.
It's not metal? This part's metal. Why isn't this metal? Why?
Because it could just go through it.
Right. If it was metal, it would go through it. It would be dangerous.
And if you touch it.
So, but Constance, back to you. What if it only had one prong? Wouldn't it still get to the device?
But it wouldn't have as much power.
Wouldn't it have as much power? Do we have any other ideas? No? Okay, so Constance is right. It does take the power from the wall, gives it to a device, but it has the second prong so that it can go back into the wall. It closes a circuit. Now, a circuit is what we do is a term in physics that we use to describe a pathway for electricity. It's how electrons go around and power things. So, like we said, we are going to power a light bulb. The first thing we're going to do is we're going to plug this in,
We're gonna
and we're going to test and see how much voltage is coming out of here. Now, from our walls, what comes out of there, if we don't do anything to it, is 120 volts of alternating current. That's how much electricity comes out of our wall.
like electricity.
Yeah, that's a lot. And so it's very dangerous, right? Most
Deadly.
things we
Like
need,
electric eel.
yeah, most things that we need don't need quite that much electricity. They don't need that much voltage. It's a lot of power. So this is called an adapter, and lots of things like hair dryers, microwaves have them, and it changes the electricity from alternating current, like I said, to direct current. So it just gives you a flat voltage. What comes out of the wall oscillates between positive and negative. It goes positive, negative, positive, negative, positive, negative, really, really fast. Okay, so we're going to test and see how much voltage is coming out of my adapter. First, we will take one of these leads, and we'll put it on one side of here, and we'll take the next one and put it on the other. Okay. And we're reading, Catherine, could you read that for me? How many does that say we have? 9.2. Yeah, 9.23, right? Volts. Okay, perfect. So now we know that there are 9.23 volts coming out of my adapter. So, now that we know we have power, let's try to light up a light. So, what was that thing I was talking with you guys about? What does electricity need to be able to work?
Electrons.
It needs electrons.
Adapter.
What do the electrons, what do they need to do?
Create a circuit.
Create a circuit. Do you remember what I said? We need to do what to the circuit? Make sure it flows, that it's complete, right? It starts, goes around, and has somewhere to end. So, what we're going to do is we're just going to, who wants to help me with this one? All right, Constance, you can come up and help.
I might get
So we're just going to take these two ends, okay? And you're going to hold this, which is what we call ground,
I saw it turn.
against this little, we're going to put it over here so they can see too, okay? Against this little wire, because wires conduct, right? Okay, oops.
It lighted up.
There we go, let's try that one more time. Okay, now hold it against there. Perfect. Okay, so it lights up. So we know that we have a closed circuit now. It comes in through one wire, through the light bulb, and it goes back into the wall through the other prong, okay? So, just to make that easier so we don't drop it again, I'm gonna put it into this circuit board. Now what a circuit board is it has a little red strip, that's for positive power, and a blue strip, and that's usually what we call ground or zero voltage. Okay, so I'm gonna put our positive voltage in the red line, and our ground, where we end the circuit, in the blue line. So let's just test it out, make sure I did it right. We put it in the board and it lights up. Okay, perfect. So the next thing we're gonna do is we are going to draw this on the board, how it should be.
Can I draw it?
Let me draw it first and then we can practice, okay?
No, I don't.
So we have our positive voltage coming out of the wall. This is just how we draw it. It goes over here and goes through a light bulb. And it comes back to that ground position. Remember where the voltage, where we don't have any more energy.
Sign and a plus sign.
Yeah, it's kind of like a plus sign. The plus sign indicates the positive energy. And this is just supposed to be like dying out little lines, right? So it goes to nothing at the end. So this is what circuit we just made. Okay, so what would happen if we took out the light bulb?
It would stop.
It would stop, right?
Electricity.
Yeah, electricity wouldn't know where to go. Would we have any electricity if we took the light bulb out?
No.
No? Yeah, where do you think it'd be?
It would be inside the cords.
It'd be inside the cord. Do you want to test that with me? Yeah, okay, come on up here. Okay, so if we take the light bulb out and we take just a regular wire to test inside the positive voltage, let's see if it's still there. We'll put this on ground and put this on the red one. So you can just clip that onto the red.
Onto where?
Onto this pin right here.
There?
On the pin. There you go. Perfect. Okay. What does the voltmeter say?
9.23.
9.23. Is that what we started with, Catherine?
Yes.
Good. So the energy is still there. Okay. So, perfect. Thank you for that. Okay. So now what would happen if we wanted to put two light bulbs in the circuit? How would we put them in? Do we put them in next to each other, one before the other? Constance?
Would you put one on the red line and one on the blue line?
One on the red line and one on the blue line. So you mean put one before the other one?
Yeah.
Okay, yeah. Does anyone else have any ideas before we try that? What's your idea? No? You don't have one? What about putting them next to each other? What do you think that would do? It doesn't make any sense?
I was kidding.
Well,
Say it again.
if we put one next to the other one.
Wait.
So we put two coming into the red.
Electricity still?
It would still make electricity, that's right. Yeah, we could do it either way. We could either put one before the other, or we could put them next to each other. The difference in that is called a series circuit or a parallel circuit. Now in a parallel circuit, what it looks like is we just put another light bulb next to the first one. And it looks like that. This is called a parallel circuit because they're next to each other. If we take out one of them, the electricity still has a path to go through over here. Or if we took out this middle one, the electricity could still go through this whole path. So they're next to each other, but they don't interfere with each other. Yes?
How would the neutrons or electrons, what would the path be if you had both two?
That's a very good question. So the electrons, do you guys like to do really hard things? Yeah. If there's a hard choice and an easy choice, what one would you rather do?
Hard choice.
You would rather do the hard choice?
Because I'm hard.
Okay, well, I guess I'm lazy. I like to do the easy way. That's what the electrons like to do too. They will go to the path of least resistance. So if we take 2 resistors and add them here, this little squiggly line I drew is for a resistor. They look like this in real life. Okay, so we're going to try it. We're going to put 2 light bulbs on my circuit board with 2 different resistors, and we're going to see what happens, and we're going to see if you guys can tell me what you think is happening. Okay, so this circuit's a little more complicated. Okay, we're going to take 1 resistor and put it in the circuit board, and then we're going to put a light bulb from there to ground. Okay, we can already see it's lighting up. So, what do you think this next light bulb will do? Do you think it'll do the same thing? Yes. Yes? Do you think they'll glow exactly the same amount?
Yeah.
All right, you guys are going to have to look really closely at this one, okay? All right, can I have someone come up here and look at these really close? How about someone, Jake, do you want to help me? All right, come on up here. Do these lights look like they're glowing the same amount? Does one of them look like it's brighter than the other one? Which one looks brighter? That one. Okay, so where do you think there's more resistance? Where do you think there's a bigger obstacle for the electrons to go through? Now, if electrons like to go where there's less resistance, they're probably mostly where the bright light bulb is, right? Yeah, because it's not as hard to go that way. In this resistor, it's a lot smaller than this resistor. It's like an obstacle, right? So if the electrons go this way, they have to jump over a really big hill to make it work. Over here, it's just like a little mound that they have to go over. Does that make sense?
Yeah.
Yeah. Isn't that kind of cool? We have the same light bulb, but they're lighting up differently because there's different resistances. Thanks, Jake. Okay, so now let's go back to what Constance said and do one in front of the other. So to draw that circuit, we'll get rid of our light bulb over here, and we will draw another light bulb right here. Okay, so this will be our circuit with 2 light bulbs in series. What do you think will happen to the light bulbs this time? Do you think they'll glow the same? One brighter? Yes, Constance?
I think they will glow the same. I think that the one on the bottom will glow more because it doesn't have a resistance.
The one on the bottom will glow more because it doesn't have a resistance?
Yeah. No, the one on the top.
The top will glow more. Oh, let's take that resistor off.
Oh, then they will both glow the same.
They'll both glow the same. All right, let's try it. We'll take 1 light bulb. Can everyone see this? And we'll put it in our circuit board. And then we'll take the next light bulb and we'll put it in the circuit board too. Do those look like they're glowing the same?
No.
They don't? Come up here and look at them. Maybe that'll help. Does that help? Do they look like they're glowing the same?
Yeah.
Yeah, they look like they're the same, right? Okay, so what this is the electricity just goes through one and goes through the other. And they're exactly the same, so the electricity is going to have the same effect on it. Okay, so we were talking earlier about what comes out of the wall, how it's 120 volts AC, which is alternating current. How do you think these lights work? Do you think there's some kind of transformer in there that makes it so our light's constant? I mean, that looks pretty constant to me, right?
There are probably wires that run from a electrical current into the electrical current runs into the light bulb through the wires.
Okay, yeah. But do you think the current going through there is alternating current, where it goes positive and negative, or direct current, where it's just flat?
Alternative.
You think it's alternating? Do you see these lights flickering at all?
Oh, no.
You don't? Does anyone see them flickering? What if I told you they were flickering? Would you believe me?
No.
No? Okay, well they are. These lights run off of our alternating current. And they blink so fast our eyes can't even see it. They blink 60 times every second. So in just 1 second, they turn on and off 60 times. That's really fast, huh? Yeah? Our eyes can only see up to about 40 times a second, or what we call 40 hertz. And so that's why our eyes can't tell. But have you guys ever watched Olympic Games when they do ski jumps? Yeah? Have you ever noticed that when they're going really slow in the air, you can see the lights behind them flashing? Yeah, you have? That's because the lights turn on and off 60 times a second. So when you put it in slow motion, you can actually see them turning on and off. Perfect.
On a bike?
On a bike? What about a bike?
On the back?
On what back?
On the back of the bike?
It depends what kind of light you have on there. But yeah, most lights turn on and off
Wait.
60 times a second.
Um,
Yes.
But if you look on the tire, it might look like there's a light on the back of the tire, but really it's the sun reflector
Yeah.
spinning, so it will look like it's
So it looks like a light? Yeah, that's right. That's just reflection. Okay, so what would happen if I took the second light bulb out of the circuit? Do you think the circuit is complete?
No, someone would probably get electrified if they were touching it.
Yeah, you don't want to touch open circuits, huh? Do you know what you need to do to fix it? Does anyone think they know what to do to fix it? Yes, Constance.
Put a wire.
Have a wire run straight through
Or
it.
metal.
Yeah, put a wire run straight through it. Do you want to come up and draw that? Perfect. Okay, and now our circuit is closed again, and the light bulb will glow. Okay, so what did you guys learn today?
That you have to have a closed circuit for electrons to run through and light the light bulb.
Perfect.